Okay, let's get into this. Today, we're really undertaking a deep dive into some serious cyber architecture.
Yeah, absolutely.
We're moving beyond just, talking about backups. We're looking at engineered resilience.
Mhm.
Specifically, diving into the architecture and security principles behind Dell's cyber recovery solution.
Right. And our mission today, I think, is pretty clear. We want to extract that core technical knowledge.
The stuff you really need to understand.
Exactly. How vaulted data is actually protected, how it's analyzed, forensically analyzed, and then recovered safely, even if there's been a really sophisticated attack.
And we're grounding this, pulling knowledge straight from the D-PCR-DY-01 training material. So this is based on rigorous standards.
Yeah, this isn't just high-level concept.
No, it's about understanding the high-value technical controls that actually make this system tick. We want you, the listener, to really grasp the strategic why behind each piece.
Precisely. And, the very first principle, it has to be about a protection from destruction, right?
Makes sense? Someone gets in.
If an attacker breaches your primary environment, the first thing they'll try to do is wipe out your safety net, your protected copies. So when you create that copy in the vault, and you absolutely need to ensure it's immediately protected against modification, against deletion for a set time, what's the specific technical lever you pull? What enforces that tamper resistance?
Okay, yeah. We hear the term immutability thrown around a lot.
We do.
But what's the actual mechanism Dell uses here? How do they guarantee that?
It is the secure copy. That's the term, the feature.
Secure copy. Got it.
And it's really the non-negotiable foundation here. Secure copy enforces that tamper-resistant retention the instant it's created.
Instantly.
Instantly. And that's vital because it stops, say, an insider threat or maybe an attacker who's stolen credentials and looks like an insider.
Right.
From just running admin commands to delete or mess with the backup set. That copy is locked down for its retention period. Full stop.
Okay, so that locks down the data itself. Great start. Now let's talk setup, the logistics. This architecture doesn't just, materialize.
No kidding.
You have to install the cyber recovery software onto that dedicated vault server. So thinking purely about getting the software installed, what are the two absolute must-have pieces of info or components you need?
Right, for the basic install, you really need two things to physically connect the software to its secure storage backend.
Okay.
First, well, obviously you need the cyber recovery installer package itself, the software bits.
Naturally.
But second, and this is crucial for connection, you need the Vault data domain's host name.
Ah, the address.
Exactly. That host name is how the software finds where the secure storage actually lives. It lets it start the configuration, link the application to that immutable storage pool.
Okay, so we've got the Vault server with the software. The secure storage is configured via its host name. But, this system has to get its data from somewhere, right? It needs to pull protected copies from production, usually orchestrated by something like PowerProtect Data Manager, PPDM.
You're right.
So what specific credential does cyber recovery need to talk to PPDM, to orchestrate creating that copy?
Yeah, this isn't like a user login. This is about API trust, programmatic access.
Right.
Cyber recovery needs the PPDM API user. It's often standardized as a cruiser or something similar.
Ooh, okay.
And this credential isn't for someone logging in to run backups manually. It's about giving the cyber recovery application the permissions it needs to talk to PPDM's API.
So it can ask PPDM questions.
Yeah, query the environment, say, hey, create this protected copy, and then stage it ready for the vault to pull. It automates the whole thing.
Makes the process smooth, automated. Okay, now let's shift to separation. Physical, virtual separation. For me, this is where the security architecture really starts to, shine.
It's critical.
We're trying to lock down this vault environment, but it still needs to replicate data in, right?
Yeah.
So what's the absolute crucial network best practice here to minimize that attack surface, prevent lateral movement?
This goes beyond just like VLANs. It really mandates physical or at least strong logical separation at the network layer. The strict recommendation is using separate, dedicated, and strictly firewalled interfaces.
Separate interfaces for what?
One for management traffic and a completely different one just for replication traffic.
Okay, but why is that separation so fundamental? Couldn't you just, run everything over a single really locked down interface? Maybe save some ports?
You could, technically, but it kind of defeats the principle of least privilege and maximum isolation.
How so?
Well, if you have separate interfaces, you can apply incredibly granular firewall rules. The replication network interface, it only allows replication traffic. No management protocols, no SSH, no web UI access, nothing.
I see.
So if your production environment gets compromised, the attacker has basically no path to jump from the replication stream over to the vault's management network. That firewall boundary between the interfaces is the critical control point. It keeps those two worlds really isolated.
That's a pretty robust architectural defense then. You've got layers.
Yeah.
Immutability for the data, network isolation.
Right. Designed to stop an attacker getting in or destroying the vault data directly.
Okay, so we've built the walls, physical network barriers.
Yeah.
But what if the data we vaulted was already compromised?
The Trojan horse scenario.
Exactly. What if the attacker was already lurking in the system when we took that snapshot? We've just carefully vaulted infected data.
This is where the strategic thinking has shifted in recent years.
Right.
We have to assume compromise might have already happened.
Right, so you need an internal check.
You need an internal security audit of the vaulted data itself, and that's where we bring in the digital forensics tool, the CyberSense analytics engine.
CyberSense. Okay, so this isn't just checking if the backup completed successfully.
Oh, not at all. It's vastly different from a simple storage integrity check or a backup catalog verification.
So what is its main job, its primary objective when it looks at that secure, vaulted copy?
Its main function is to analyze file metadata and the actual content looking for signs of compromise.
Signs like?
Like corruption, or specifically signs of ransomware. It's doing deep file-level introspection, not just looking at the container, but inside the files.
How does it do that?
It looks for things like weird changes in file names, shifts in file entropy, that's a measure of randomness.
Which encryption causes.
Exactly. Encryption dramatically increases entropy. It looks for these digital fingerprints that basically scream, this file was hit by ransomware. A simple storage scan wouldn't see that. The container might look fine, but the content is garbage.
Okay, that sounds intensive. Doing that deep analysis, checking hashes, entropy, potentially across terabytes or petabytes of data.
It is definitely resource intensive.
So before CyberSense can even start churning through all that data, what needs to happen first? What's the prerequisite step on the analytics engine itself? What does it need access to?
Well, the analysis host obviously needs access to the data it's analyzing, but critically, it can't risk changing the evidence.
The forensic principle. Don't tamper with the evidence.
Precisely. So you have to mount the vault data domain copy, but typically it must be mounted in a read-only state.
Read-only. Absolutely vital.
Absolutely vital. You're doing forensics on that copy. You cannot risk contaminating it, or maybe even accidentally triggering some dormant malware that might be sitting in that compromised data. Read-only is non-negotiable for analysis.
Okay, read-only mount. Got it. Now back to that resource intensity. That compute requirement sounds like it could be massive, especially if you need results fast after you think you've been hit.
It can be, yeah.
So if you need to process huge volumes of data efficiently, what's the single most critical resource for driving CyberSense's performance? Is it network? Storage speed? Something else?
It's a classic compute bottleneck scenario, really. Network speed matters for getting the data to the analytics engine, sure, and storage speed helps feed it, but the actual processing is where the time goes. So what's most critical is having sufficient CPU and memory on the analytics host.
CPU and RAM.
Yep. This thing is doing heavy mathematical lifting hashing, entropy calculations, pattern matching across potentially millions or billions of files. If you skimp on the compute power,
your analysis grinds to a halt.
Exactly. Your analysis engine becomes the bottleneck. And that means your time to detection and your time to recovery just stretch out longer and longer. You need serious horsepower for that deep validation, especially at scale.
Okay, makes sense. So CyberSense runs, it does its deep forensic scan. Now, the administrators are looking at the results. What are they primarily monitoring on that CyberSense dashboard? What clues tell them about the integrity of their copies?
Their focus shifts completely. It's not about backup success-fail anymore. It's a forensic view. They're looking closely at anomaly scores, specific file corruption alerts, and just the overall integrity status CyberSense assigns to each vaulted copy or snapshot.
Anomaly scores. So it flags suspicious changes.
Yes. They're looking for spikes in that score, which can help pinpoint the exact moment or the specific snapshot when maybe a ransomware payload was introduced or when some destructive script first ran. It helps narrow down that window of compromise significantly.
Very useful. Okay, let's pivot back slightly to security architecture, but focusing on the human element, the controls. Even with all this tech, people need access, right?
Always.
So Within the cyber recovery solution, is there a specific user role responsible for managing things like multi-factor authentication, MFA,
Yeah.
enforcing those tight access controls on the vault itself?
Yes, there is. That specific security responsibility is assigned to the Cyber Recovery Security Officer. The role name is usually CRSO.
CRSO, okay. And why a separate role?
It enforces that crucial principle of separation of duties.
Oh.
The idea is that the person or team managing the day-to-day backup operations shouldn't necessarily be the same person controlling the security gates, like access controls and security policies for the vault itself.
So the CRSO manages the locks on the vault door, essentially.
That's a good way to put it. They manage MFA enforcement, password policies, user access to the vault management interface. It ensures that even if, say, a regular backup admin credential gets compromised, accessing the vault's critical functions still requires that second factor managed by the CRSO.
So one compromised identity can't just walk in and wreck the place or change security settings.
Exactly right. It aligns perfectly with applying zero trust principles, even within your last resort recovery environment.
Okay. And that brings us finally to the end game. The whole reason this exists. Recovery after an incident.
The moment of truth.
You've been hit. You've hopefully got your clean, isolated vault. CyberSense has done its deep analysis. Now you're prepping to recover. After all that analysis, what is the single most crucial piece of information CyberSense gives the recovery team in its forensic report?
This is fundamentally the entire point of the exercise. The most critical output, the golden ticket, is the identification of the most recent known clean snapshot or copy for recovery.
The known clean copy, not just the latest copy.
Precisely. This is what changes recovery from, a series of educated guesses.
Like, well, maybe the snapshot from 48 hours ago is okay. Let's try that.
Exactly that gamble. CyberSense aims to replace that guess with certainty. It provides the definitive timestamp, the specific recovery point that its analysis has validated as clean before the detected compromise occurred.
And that minimizes the risk
of restoring an already compromised state and just reinfecting your production environment all over again. It's about ensuring you recover clean.
That certainty, yeah, that really changes the whole recovery planning conversation, doesn't it?
Absolutely does.
What strikes me here, thinking about the source material, is the conceptual shift this whole architecture represents. It highlights that modern cyber resilience isn't just about, having a copy somewhere else.
Right. Having an offsite backup is just table stakes now. Expected.
Yeah, it's about creating this segregated, isolated, hardened environment where you can actually perform reliable digital forensics on the backup data itself before you even think about restoring it.
It really elevates recovery, doesn't it? It moves it from being purely an operational task, get the data back online, to being almost a forensic exercise first. Is this data safe to bring back online? And if you're running, say, a highly regulated business or dealing with incredibly high-value data, that assurance, the guarantee that your recovery point is genuinely uncorrupted, becomes, arguably, more valuable than just the raw speed of the restore itself.
That leads to a pretty important question for you, the listener, to think about, doesn't it?
Yeah.
If your current recovery plan only relies on, say, basic integrity checks or checksums from your standard backup tool, how truly confident are you that you wouldn't just be restoring malware or ransomware right back into your network? The integrity of that known clean copy, validated forensically. That seems to be the real dividing line now between just disaster recovery and genuine cyber resilience.